Okay, we're at pretty much the end of chapter 9, and we've got just a few things left to do, but they're really important. One is to define the terms effusion and diffusion and take a look at something called Graham's law and how that relates to it. So we're going to start with the idea of effusion. Okay, if I have gases that are separated from each other and I have a very tiny place for them to be able to mix through each other, um, the lighter gas is going to pass through this opening faster. We say it effuses through that faster. Now, likewise, we also have something called diffusion. Okay, so effusion is going through a very small opening. Diffusion is where a gas spreads out. Now, think of opening a perfume bottle. Okay, now we will look and see how fast a molecule is going, but it's going over 1,000 miles an hour, somewhere in that range. So if you're 20 feet away from somebody opening a perfume bottle, why don't you smell it instantly? Well, that's because as this molecule goes, it's going to go until it hits something, and it's going to go and it's going to change directions. It's go again, and it's going to hit something and go again. So the mean free path, the path that it goes between collisions, isn't that big. So it's, even though it's going really fast, it doesn't move throughout the substance near as fast. Now, the lighter it is, the faster it's going to diffuse. Okay, just like the lighter it is, the faster it is going to pass through a tiny opening for effusion. Okay, here's an example of effusion. Here we have a helium balloon and an argon balloon. And when we look after a bit of time, the helium has escaped through the pores in the balloon quite extensively, decreasing the volume. And if we look at the argon, it's all still there. It didn't live up to its name. Otherwise, it would be argon. Okay. So we can use diffusers to do a number of things. Here is an example of separating your enriched uranium from depleted uranium. Okay. And there is a law, Graham's law of effusion, that says that the rate of the effusion of one gas to the rate of effusion of another gas is proportional to the inverse of the square root of their molar masses. Okay, so in other words, the rate of gas 1 to the rate of gas 2 is equal to the square root of the molar mass of gas 2 to the molar mass of gas 1. Fairly simple. Again, you just have to keep track of everything, and it's a fairly simple calculation to do. I would say easy, but I know how easy it is for people to take something simple and say it can't be that easy, and you make it hard. Okay. We also want to look at the kinetic molecular theory. Okay, and some of the background of the kinetic molecular theory is that we can do a lot of variations to gases. We can heat a gas, we can compress a gas, we can do a lot of things. So there's a bunch of different manipulations we can do with gases, but what we want to do is look at what does that mean, okay? How fast are these molecules going? So this is one of our questions that we have. Now, if I say, what is the average velocity of these molecules? It doesn't tell me a whole lot because there's some molecules going one direction and some molecules going another direction. And overall, those directions are going to cancel out, finally giving us a average velocity of about 0. So instead, we take a root mean square velocity. Basically, you take the velocity, square it, take the average of all those squares, then take the square root of that. Now, without going through the derivation, the root mean square velocity is equal to the square root of 3RT over m. Now, R is our ideal gas constant, and in SI units is joules per mole Kelvin. And since a joule is a kilogram meter squared per second squared, you need to have your molar mass in kilograms in order to calculate correctly that value. Okay. Now here is a plot of root mean square speeds of a number of molecules, and this is oxygen gas at 327 degrees Celsius. And here we see the distribution of them. It's not a completely symmetrical, it's not like a total bell curve. And we see this distribution with all gases. Now, as I heat the gas, I am going to shift the average to the right, okay? And just as if I have a relationship between the kinetic energy of a gas and its temperature, it makes sense that the kinetic energy, which is equal to 1/2 mv squared, the molecules don't get heavy when it gets hotter, they just end up going faster. So that makes sense. As it increases in temperature, I increase the speed of the particles. Okay, here we see nitrogen at a number of temperatures, and you can see how the curve flattens out as it gets to higher and higher temperatures. Okay. Likewise, we can compare gases, and lighter gases are going to be moving much faster than heavier gases. For example, helium, very small, is going to be moving far faster than argon at the same temperature. Okay. Now, I just want to remind you, now this is in the book, The Kinetic Molecular Theory of Gases. I'm not going to read through all of these, but what I do want to do is separate this into two different things. Now, with an ideal gas, we make a couple of assumptions. We assume that there are no intermolecular forces and the molecules occupy no volume. Now, the kinetic theory is the one that says everything is made of tiny particles that are moving and have elastic collisions. Now, looking back here, you can see both of these are all mixed together into the kinetic molecular theory of gases. However, when we try to take advantage and look at a real gas, we really are looking at these two assumptions that we have here. And we will look at that in another video.